Henry. Okay, LADL. You may have heard this. It's an acronym for Logic as Distributive Law. This grows out of work that I've done with Greg over many years. That's in fact how we got to know each other, was by working on this sort of stuff. Haskell Curry was a logician in the 30s. Howard was another logician, I guess 40s and 50s. They have this big idea that propositions in logic are types in computer science. So the original example was this one. So you've got implicational fragment of intuitionistic logic. There are two ways of generating axioms. So any choice that you make for X, Y, and Z, there you get an axiom for that choice. And then modus ponens says, if I have a recipe for turning an X into, well, if I have that X implies Y, and I know that X, then I can derive that Y. So these two things together, the axioms and the rules, give us a system of logic, and we can prove all sorts of things in this logic. Curry and Schoenfinkel, another logician, noticed that these axiom schemata are also ways of writing programs. So in this case, this is the axiom schema, and then down here I'm writing a program. Now I'm using ECMAScript 6 because it's got pretty concise syntax for things of this sort. It reads in a value A of type Z goes to Y goes to X, value B of type Z goes to Y, and a value C of type Z, and then produces an X by composing them like this. So C is of type Z, we feed it to A, and then we get something that's expecting a Y. We feed C to B and get something that is a Y, then we feed that Y to this thing and get something that is an X. You notice that C is used twice. So here it relies on the fact that you can duplicate chunks of data. That doesn't universally hold. You know, if I have a hard drive, I can't use a program to duplicate my hard drive. I have a keyboard, I can't duplicate my keyboard. So there are things called linear resources that this doesn't apply to. But this program has this type. So it was an axiom schema, and now it's a type for a program. Similarly down here, much easier example, the axiom X goes to Y goes to X. We can represent it as a function that takes an A and a B and just returns A. So this Curry-Howard isomorphism between propositions, axioms in a logical system, and types in computer science is well known, pretty well understood. Lots of web pages about it if you want to go read up on it. To be more explicit about the way that it's a proposition, here's a little program. I'm calling it num. It takes in something that we're calling n. In JavaScript, there aren't any types per se. You just have values. So this thing is going to filter out all those values that aren't of a particular kind. You know, we might usually think of mapping it to true and false. In this case, if it's a number, it returns it. So it's the identity function on numbers. Otherwise, it throws an exception. So anything that gets through without throwing an exception, we know is a number. So in this case, it's a filter. We can think of these propositions as filtering out everything that we don't want. And so these programs are expressing propositions about JavaScript values. Now, it can be any kind of JavaScript value. Again, here, arrow takes in two contracts, or two type guards, A and B. And then it takes in a function, f, and it wraps f in A and B so that it says, if you give me a value A, what you'll get back is, first I apply the type guard big A to little a. Make sure it's of the right input kind. Then I apply f to that, and since big A is the identity on all the right stuff, it's going to compute f of A, and then we're guaranteeing that the output of f is of type B. So by filtering the input, filtering the output, we've now written this top part is a contract for the arrow type A goes to B. we've written a type guard for this arrow type. If I say contract in this context, I'm talking about Eiffel's uses of the word contract. So a guarantee on what the input and output type are, not necessarily a contract on the blockchain. So in math papers, in logic, you'll often see this set builder notation. Probably learned about it in high school. This is those things n such that number is the type of n. So this is just that same program that I wrote before expressed in slightly different notation. Or those things f that for all inputs of type A, f of A is of type B. So this set builder notation builds up the set of all functions of type A goes to B. In Python, they introduced this thing called list comprehension. So here, it says those n that come from this list, this is a variable here named list, if type of n is int. So it's slightly different from JavaScript, slightly different syntax, but the idea is the same, that I'm filtering this collection of terms and picking out just the ones that are integers. Wadler saw, hey, this is cool syntax, and in fact, we can generalize this. So he introduced in his paper, Comprehending Monads, this syntax where if we put a bracket around it, we're using the monadic return, the monadic unit, that takes a value and applies the unit to it, whatever it is. It doesn't have to be a list monad. That's what inspired the syntax, but it's generic for the monad. Similarly, if we have f of x where little x is drawn from big X, that's just mapping the function f over the big X collection. If we have two of these clauses here, then that's the monadic join. So this is composing, sorry, that's not composition. It's just applying join to y. Typo there. So monads are just a design pattern, but they have a kind of, because it's the first weird design pattern people run into when learning Haskell, they've got this mystique to them. A really fairly simple design pattern. And the things that you can do with the monad turn out to be nicely expressible in other ways too. So in particular, I've got collections as interfaces. We can express the notion of a collection by defining a Java interface that talks about the things you can do with your collection. We can define it as a monad, like the list monad. We can define it as something called the Lavere theory. Bill Lavere was a mathematician. 1963, he unified what was called up until that point universal algebra with category theory, and showed that if you have a presentation that includes sorts, which you can think of as data types, function symbols, which are methods acting on those data types, and equations, axioms that they have to satisfy, then you can generate a category that completely captures the notion of what it means to be a particular data structure. In this case, this is a free commutative monoid, but you can think of it as being like a finite set. So we have a bunch of atoms here, and each atom we can turn into the single element set containing that atom. We can construct the empty set, and we can take the union of sets. Then we have some laws about what union has to satisfy. If we do that, then we can implement this interface. This looks very much like a Java interface. An implementation of it, on the other hand, picks out a set of values for S and a set of values for A, some functions between them with the appropriate types that satisfy these equations. So given a presentation like this, we can generate a category, then take a Cartesian functor, that is one that preserves Cartesian products, into set, and each such functor picks out a different implementation of that interface. So we can not only describe collections using monads or Lavere theories, we can also describe programming languages. This is the programming language for the SK calculus that I just showed a little earlier. Here we have a sort T for terms. We have little s and little t for the source and target. Now T here, the terms of this language are not just the SK combinator expressions themselves, but really the edges in the graph of rewrites between those. So when you see T here, you should think of an edge in a graph. Now each vertex in the graph has a self-edge. So we're basically representing the vertices by their self-edges here. So this says, given any edge, I can pick out the self-edge that corresponds to the source of the target. S and K themselves have a self-edge. They're there by fiat. This is application, that if I have two edges, I can put them in application context. Because SK calculus obeys the tenant correspondence principle, or it's confluent, it doesn't matter which side reduces. So it makes sense to put two edges in the two slots of application. Means, do I do this reduction first or this reduction first? It doesn't matter. Sigma and kappa are the things that we would usually think of as edges. It's the thing that takes S, X, Y, Z to X of Z applied to Y of Z. And that is captured over here in the equations. Kappa is the rewrite rule for K. So this says the source of the source is the same as the source of the target is the source. Target of the target, same as target of the source is target. These make sure that our edges behave the way that we want them to. Then we have the explicit things for the edges that we introduced over here. The source of sigma is S applied to X, Y, and Z. The target of sigma, when we can, this sets the preconditions for when we can do a rewrite using sigma. This sets the post-conditions of what happens after the rewrite. So here you can do the same thing. This is a very, very minimal example. S and K really aren't what most people are familiar with, but you can imagine if I have constructors here that introduce parts of the state of a virtual machine, and then down here I have ways of updating that state. And over here I have the source and target, what it means to be a source and a target, and how the state gets updated. You can see that I can capture the whole operational semantics of a programming language. It's just writing the virtual machine. This is a language for it. If you go and look at projects like Mod or K-Framework, they're all about writing down operational semantics in a style very similar to this. TypeScript, among others, has a notion of a structural type. So if our propositions are types, what do we want our proposition language to look like? And we're going with something called a structural type to begin with. So this is a piece of data, a JSON object. The guy's got a name, an age, an address, street number is 123, and some avenue. The type of this thing is formed by using exactly the same syntax, but in the place of the literal values, where we said Joe Schmo, we now have a collection descriptor, a type. So in this case, it's string. For age, it's number. For address, it is this more compound type. We can go down, but to write down that type, we're using the same syntax that we did to write down the instance of that data type. So structural types are a way of combining the syntax of writing down a program value, some value in your language, with extra syntax for describing collections of data. So the way to get this is we take the Lavere theory that's describing the programming language and combine it with the Lavere theory that is describing the collection. We can use either one interchangeably. We started back here, we started with the syntax of the term language, dropped into the collection language for string, popped back out for the term language again at age, went down. We're going back and forth between them. So here, we want to be able to do the same thing. To do that, we identify two of the sorts. We're going to say, these two things that were different in the theories we're now considering to be the same thing. And then we just take the union of all the function symbols and equations. So for example, here is a Lavere theory of a monoid. If you're not familiar with the term monoid, it's like string concatenation. It's anything where you've got two values and you can stick them together. That has an identity, and the way that you put them together is associative. So in this case, consider I here to represent the empty string and tensor to be concatenation. Or we could take I to be 0 and tensor to be plus. Or we could take I to be 1 and tensor to be times. Anything that satisfies this interface qualifies as a monoid. Unit laws here that say identity behaves the way you want, associativity makes sense to multiply in any order. Here is the theory of peano-arithmetic. This is a very small way of, essentially it's unary. Right? How do we get numbers? You start with 0, and then you can add 1 to it. So expressions in the theory of peano-arithmetic are like SSSZ to mean 3. So now when we combine the two, whereas before we had M and N, in the combination, we're calling the sort T. So now they've been identified. But we have all the possible function symbols, both for the monoid as well as for peano-arithmetic. But now we can think of this thing as being the empty list. And this is concatenation. This is the list containing 0 and successor. They still have to, the lists still have to satisfy these rules for concatenation. So here's an example term from the resulting language. We can alternate back and forth between peano-arithmetic or list notation. Bounce back and forth and back and forth. So this is a particular value in the resulting language. But this is also, to some extent, a type. This particular type identifies a singleton value. And the reason we wouldn't normally think of this as a type is because we don't have expressions in the collection language for more than just these singletons. But if back here in monoid, we also added in an extra symbol that said anything goes here, like a top symbol. Then in this expression, instead of one of those Zs, we could put a top. And it would say any pattern that matches this, and right there we just bind to whatever subtree is in that pattern. We could also add built-in filters. And instead of Z here, we could say string or int or something like that. So I've built up this structure that's describing both terms in peano-arithmetic, collections, which are monoids. You put them together, you have lists of terms, bouncing back and forth. Now, let's see. Yeah, this slide should have been earlier. In order to interpret a structural type, we have an expression that is denoting a collection of terms. Right? A structural type is just an expression in this combined language. But on the other hand, what we want it to mean is some way of assembling a whole bunch of terms together. Which are the things that pass that filter? So in order to get collections of terms, instead of identifying the sorts, we take the union of them. Then we add the function symbols and equations as before. And then we add one more function symbol that lets us turn a term into a collection. Basically form the singleton containing that term. So here, the composition of them is a theory that has two sorts, M and N. Down here, we can form natural numbers as before. We can turn them into the singleton list containing that natural number, and then we can form lists by concatenation. So the only kinds of things that show up in this theory are actually lists of integers. So whereas before we had a language for expressing what we meant by a list of integers, here we actually get lists of integers. coming out. When we sum theories, this notation here is coproduct. T is for terms, C is for collections. When we apply that to a particular set of values x, what we get is a set of atoms x. What we get is the set of atoms that we just take as elements by fiat, plus T of x plus C of x, and all possible combinations of T's and C's interleaved back and forth with each other. And we sum together this entire list of, this entire infinite sum of sets. Now, the distributive law in the title is something that goes from terms over collections to collections over terms. So on the left here, we've got a structural type. It's one of these arbitrary alternations between terms and collections applied to some set of atoms x. Sometimes we'll take that to be empty, so that the only vertices in the graph that we're generating are the ones that have to be there, rather than assuming a set of built-ins. So x might be empty, but it works for an arbitrary x. So we start with this, and then we have to get it over to this form. Given an arbitrary formula, arbitrary structural type, how do we turn it into an actual collection of terms? Well, here, because T and C are monads, we can do the join on T there, we can do the join on C here. So then we get a strict alternation, TC, 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 etc. Then we can apply the distributive law here that swaps the order. We can push the C's to the left. So in this case, TC goes to CT. Then we can apply the joins again, and no matter what collection of C's and T's, however they alternated in the structural type, we can turn it into a collection of terms. So this is giving us a way of generating from the syntax of any programming language with a choice of a collection, a notion of how we want to group these things together, and given a distributive law, these don't always exist, I can give you an example later, but if you've got a distributive law, a way of swapping the two, then we can generate a type system. We know how to interpret the structural types as collections of terms. Since our structural types are propositions, this gives us a logic by which we can reason about these collections of terms. Here's yeah, go ahead.
So there's some important points here that logicians and other people might care about. One is that the kind of logic that's generated is exceptionally well behaved. In particular, there's a program in logic called realizability. So what realizability asks of the logic is that the meaning of the formulae is just the collection of programs that bear witness to that property. And would you mind going back one slide? And that's exactly what happens here, right? If you look at the far right-hand side, the meaning of any structural type is exactly the collection of terms that bear witness to that property. So it's not just that we auto-generate a logic, we auto-generate a logic that is sort of best of breed in the sense that it is realizable. It's also automatically in alignment with Curry-Howard. It also, when we go to the proof theory, the idea is that it will automatically have a cut elimination theorem, which is, I mean, Mike hasn't talked about that, but it's another best of breed quality of logic. So it's not just that we're turning a handle and getting some logic out. We're turning out a handle and getting a logic that has exactly the properties that people have been looking for when they design logics by hand.
Thanks. Also, at this point, this is the sort of type system that currently exists in Mercury. We've got the ability to match against any structure. So the patterns that Kyle was going on about, these are our structural types. So these patterns are the things on the left, and then the things that those patterns accept is the collection of terms on the right. So this is how the pattern language matches up with what we've been talking about here. So here's an example of a very simple structural type. Once you introduce the logical connectives that Kyle said he's working on, going to be in within the next couple of weeks, this says, I want those terms, and this is using the language of monoids, those terms that are not the identity, and they split up into two pieces, neither which are the identity. Oh, I'm sorry. It's not the identity, and it can't be split up into two pieces where both of them are not the identity. So it's neither one nor a composite number, and those are the primes. But this works for an arbitrary monoid. So if you go look at the monoid that we've got with par, right? Par is a monoid. You can put things together, just par them with each other. It has an identity that's nil. So this ought to work for par. What do we get? Well, if we replace this thing with par, and we support not and I with nil, what this gives us is the atomic processes, that is, single-threaded processes. It's either a send or it's a receive, or a nu with the body inside, because you can't pull apart a nu without. Anyway, it's the atomic processes, the single-threaded stuff. So this is a very useful structural type that that works even in the case of programming language. Next, after this, we want modalities. Modalities are what let us talk about the behavior of programs and not just their structure. So at the top here, we've got this diamond modality. It's usually pronounced possibly. So if we have a filter A, a proposition A, then possibly A describes those edges in the graph such that, oh, I'm sorry, this exists shouldn't be there. Let me fix that one. It's those terms A whose target satisfies the proposition. No, it is S of A. Yeah. Sorry. There we go. It is the sources of those edges whose target is in A. So if you have some subgraph identified by big A, then this picks out the subgraph of things that are one step removed from it. So possibly here means it is possible to evolve into something satisfying big A in one step. So it lets us pull out more and more and more. If we add a little asterisk to the possibly diamond, then it's whenever it is eventually possible to reach something of type A. So if you have A expressing some kind of desirable state that you'd like to get into, this picks out all of those processes for which it is possible to reach that desirable state. Instead of diamond, you can turn it 45 degrees and get a box that's necessity, and you switch and exists for a for all, and it says, we will always get to this desirable state. The next line here, we're generalizing the possibility to include a context and two types. So to read this off, this is those terms T for which there exist terms U and V of types A and B respectively, and an edge W, where the source of the edge is T and U being in a context together, and the target of the edge is V. So if we take as our context application, so it's the terms T that when you put them in context with U, you get V, or it's possible to get V. Okay, this context has two holes. In one of the holes you stick a T, the other you stick U. and then you let it go, and it is possible to evolve over one step to get to V. U is of type big A, and V is of type big V. So you know something about the thing that T is butting up against, and you know something about what the two of them together evolve into. So then if we have application as that context, and think application in any functional programming language here, we use that. This says, I want all those terms T that when I apply them to a U of type A, I get something of type B. That is, we have characterized the arrow type A arrow B. Okay? If you've got something of type A arrow B, you apply it to an A, you get a B. That's what this thing is, specialized to that two-hole context. But in Rolang, we don't have application. What we have, well, we do in some method calls, but for the most part, what we have is par. This says if we put a term T in parallel with a term U, and then they interact with each other over whatever channels they have in common, they evolve to something, V, that satisfies the predicate B. This is very different from application, because with application, there's a clear distinction between the function and the data you're applying it to. Here you've got two processes. Par is commutative. You just set them down next to each other and say go, and they interact until they result in this thing. It's also a possibility, because they may, non-deterministically, may go off to C, but at least this is saying, give me those things where it's possible to go to B. This is Luis Caire's rely guarantee mechanism, that if I can rely on this thing satisfying some properties, then when I put them in parallel, they'll only evolve to this other thing. I guess in this case, the rely guarantee would use necessity rather than possibility, but they're very related.
Again, this if you're not familiar with the logical literature, it's hard to understand the import of a result like this. No one in the literature, to the best of my knowledge, had ever suspected that you could unify the modal types with the arrow types.
Yeah, this is a new result that we haven't seen before. Also, every behavioral type system we've ever seen has been constructed by hand to match the term language. They stare at the term language long enough, sort of figure out what it's doing, and then invent one. This generates one. So it's totally algorithmic once you've chosen your notion of collection and once you've given a distributive law. The modalities make use of the monadic language here. You see, I've got this expression in set builder notation. I can use that same Wadler monadic comprehension notation for expressing this stuff. So here's an example of a behavioral type that is useful. It is not possible that there exists a channel X such that the process I've got sends my special don't leak channel on it in parallel with anything else going on that, actually I don't need this not nil, in parallel with anything else. So if the compiler can prove this statement about your code, you know that your value can't leak. It's a very concise way of saying, this is the stuff I care about, make sure it never leaves my program. You can express liveness properties, you can express absence of race conditions. So you got the DAO contract, there's a race to the bottom. Greg has written up a nice paper that uses this same sort of language. You can go find that on the web, but shows how had they had this language and been able to express we don't want any race conditions, it would have prevented the DAO attack because they never would have deployed it. Their implementation would not have compiled, it would have failed the type check. So this is our vision for what Rolang is to become. Right now, we've only got the structural part. For Venus, we're hoping to get the modalities and bring this full, rich language and type-checking algorithms to bear on your contract so that they will be provably secure.
Can I ask a question just on this slide? I'm sitting over here.
Yeah, there, thanks.
What is being existentially quantified in the second line
This
there?
one here.
Yeah.
It says there is an edge U that satisfies the proposition A. There is an edge V that satisfies the proposition B. There's an edge W that is arbitrary, such that the source of W is of this form structurally. It's this context with those two things filled in, and the target of W is V.
So both the U and the V are being existentially quantified?
And the
then,
W.
Okay, thank you.
Is that it for you?
Yeah, I think that's it from me, but I'd like to answer questions if
Sure.
there still are.
I got a question.
Hey,
So
Dan.
the getting to Venus or whatever, is it just writing Scala to do the type checker, or is there some part of this that's actually not figured out?
Well, these modalities, we know how to define them, we know how to write them down. Doing the type checking is non-trivial, right? There are undecidable propositions that you can express using this language. Figuring out what subset of this language is decidable, what subset is polynomially verifiable or linear or sublinear, all the complexity classes of verifying these types is open research. We've got lots of researchers that have signed up to work with us on this sort of thing.
Do you have any examples of what something
Luis
you might leave
Caides-
out? Oh, sorry.
Luis Caides, in his behavioral type system for the pi calculus, can be very easily adapted to Rolang, and he proved a bunch of decidability properties on those. So we're probably going to leverage all of that work to get at least some subset of types that we know are provable. We're
And
also intending, sorry, just a
Yeah, go
second.
ahead.
We're also intending, as Pyrofex, to put up a whole bunch of hardware that you can throw at this problem. So up until now, type checking has been something that needs to be really efficient because you need to do it on one machine. But if you've got a data center that can prove that your program satisfies the type, you can write much more expressive types. Great.
And I mean, the way this was done in the past, like with model checking or other kinds of symbolic execution, which is effectively what this comes down to, is for those undecidable things, you give it gas. You get to run the check for X long. And if it comes back all checked, you're good. And if it doesn't, well, you don't know. So basically what you get is some sublanguages for which you know it's decidable. Awesome. That's great. And there are already existence proofs that there are interesting sublanguages, expressive, interesting sublanguages for which these kinds of checks are decidable. And then there are all these other languages, the supersets of these decidable subsets where we don't know. So it's still useful to write down the properties and then go see what happens.
So one illustration of the difference is a decidable set is one where you know how long it's going to take you to figure out all of the elements in the set. An undecidable set, you have no guarantees, but there's something called computably enumerable, where you can run the program and it'll spit out elements as it discovers them, and you can be sure that those ones are in the set. So if you've got a program, you let this thing go and you wait and see if your program is one of the ones that pops out as it's trying to do its proof.
This generalized diamond modality
Yep.
is, so you're saying it's a canonical term that you can construct in one of these.
If you have any, if all your function symbols are unary, then you can't construct it because there's no two-hole context. But if you have any n-ary function symbols for n greater than or equal to 2, then you'll always be able to pick a context and construct that thing.
In the process calculus literature and sort of folklore, one of the things that was always a desideratum was to design your reduction rules so that there were no heating rules. and a heating rule was a unary evolution. Whereas, like in the pi calculus, the rules are all about, you can subdivide the term into two parts, and that's an interaction style rule, which is, so that was considered the gold standard. And so that's why the two-hold, that's sort of really the origin of the two-hold context. Most, like the lambda calculus is also like that, right? Yeah, so it's not an onerous constraint.
Christian, I think he...
Thanks. So it's actually just based off of what you guys were talking about, the question before. So the first question I had was, is there going to be compiler flags, essentially, to allow you to pick which subset of proofs you want the compiler to actually go through? Or is the plan just to, I guess, eventually solve that all the way through? So that's the first question. Second question, and I'll let you take it from here. Is there any plan to actually have cloud infrastructure to do that compilation if... Yeah. I mean, I don't know if that's something that's a part of what PowerFX is working on.
It's beyond Mercury, so we don't know exactly what we're going to do. Compiler flag seems totally reasonable. As far as the infrastructure, it is PowerFX's intent to put up hardware and then charge people for doing compilation tasks on it, as well as to allow other distributed players who want to be in this compilation game, who can come in, do the compilation. If everybody agrees, then everybody gets rewarded. Cheaters are punished. A Casper-like algorithm for doing validated compilation. Trying to set up something like that.
Are you actually looking at doing the compilation on-chain?
Compilation on-chain can be done. It would be very expensive. Greg would certainly like to be self-hosting to the point where you can run the Roland compiler on-chain. So it could be done. Whether it's worth doing or not is another question.
So I have just a few addenda to add to Mike's most excellent talk.
Come on up.
Okay. Thank you. I can just use that, yeah. So I think the use case of type checking contract code is a very compelling use case. And the DAO bug is just one example of lots and lots of examples where being able to type check smart contract code is a very compelling use case. So already, it's a slam dunk. We should have a feature like this from my point of view. But I want to talk about some of the other use cases once you have one of these. So first of all, if the blockchain takes off, then you have the world's, you have a decentralized GitHub, right? Because you have all this contract code up on a immutable store. And so now what we have, is the situation of are we planning for success? Because that's another way you can fail, right? You can succeed so well that you're overwhelmed by your success. And so one of the big questions is, I've got all these contracts up in the cloud. How do I find what I want to find? Right? Well, how do I find the interesting contracts? And if you think about it, code is, the phrase I like to use is code is sort of the dark matter of the internet, right? Because it really is a data asset. Whether you're talking inside the enterprise or outside of the enterprise, say in GitHub, code is a data asset. But it's not searchable like other data assets. And like in GitHub, we search socially. Hey, I know a guy who knows a gal who knows this library, right? Oh, great, awesome. Well, I want to check that one out and see if I can use it in my application. It has been already imagined for many years, the idea of using types to search. So you can think about a type checker as a search engine kind of tilted on its side, right? The brain dead algorithm is, just walk up to the store, and which is a store of programs now, and return all of the code that type checks, right? This is pretty cool, yeah.
It's called Hugel for Haskell. But,
yeah.
But
So
the thing about Hugel is if you ask for a function from list of integer to list of integer, you're just as likely to get identity or shuffle as you are to get sort.
exactly. Whereas with these types, they're much more expressive. So if you just look at the structural side of things, they are. It kind of has X-ray vision into the structure or the shape of your programs, right? So now you can say, find me all the Rolang programs that are single-threaded. Or more likely, what you're looking for is find me all the Rolang programs that are not single-threaded, and I see this race, right? So there's an example of the kind of search characteristic that you could get with these kinds of properties or propositions or types, right? So that's an important use case. It goes considerably further. One of the reasons, one of the strong drivers for this work to have it at the level of generality that we've expressed it is we want to be able to do this for lots of different kinds of systems. Mike pointed out to me a year or two back, hey, take a look at JavaScript, right? I mean, JavaScript is not typed, and that's very costly to most organizations. And so the big three have taken on themselves to produce typed versions of JavaScript, right? So Microsoft, Google, and Facebook have all produced typed versions of JavaScript because they couldn't afford not to. Right? But so they've spent tens of millions, if not hundreds of millions of dollars developing these versions. They're not uniform. And there's all the promotion and all of the interoperability issues around having these multiple different versions. With this kind of system, you can literally provide a K-framework style specification of JavaScript and say, hey, I want to use sets as my monad, press a button. Oh, well, you need the distributive a lot too. You press a button, and then out pops a typed version of JavaScript, potentially saving the industry hundreds of millions of dollars, right?
The other thing about that is that when you've got a behavioral type for JavaScript, you can then ask the question of unification with behavioral types from other languages. If I've got Rolang code and I want code that behaves this way, I'm happy to call off chain perhaps to get it to work, or maybe I've got a system contract and it'll work with Node on the back end or something. I can do a query with a behavioral type, and if we can get those two behavioral types, the one from Rolang and the one from JavaScript, to unify, then I know I can call out to this code in whatever other language we've got formal semantics for. So that gives us also a model for monetizing open source. Anyone on GitHub who puts up their code can say, I'm in, and then we charge the fee for linking, doing this unification process, pulling it in, and we give a cut to the open source author.
Again, a very, very compelling use case in my opinion. And I think also in the opinion of people building cryptofex, because that's your business, part of your business plan, yes? Yeah, awesome. So I think that's another reason to get this done. So I also want to talk about some pie in the sky kind of reasons to do this. Another aspect of the generality of this is that you can apply it to, a broad range of algebras. So in the last, 15 years, the Clifford algebras, sometimes known as the geometric algebras, have been utilized in physics and in the physics community and the graphics community as a better way to reason about, to do calculations about geometric information. So now the thing is that you can run the LADL algorithm on the geometric algebras, even though they don't have rewrite rules. And you can get a query system for geometric information. Now, what emerging application space needs query for geometric information? I don't know, maybe self-driving cars? Right, so now we auto-generate a query language for reasoning about geometric information. Right? before these kinds of queries, you couldn't even write them. You couldn't contemplate writing them down. Now we not only have a way to write them down, we have a way to auto-generate the query engine that serves this space. So that's another example of the use of this kind of algorithm. And in fact, in 2009, I gave a presentation of 4 impossible queries. And I just want to mention one more of them, which was what started, this was the source of this line of reasoning for myself. It has to do with biology. So it turns out that back in the early 2000s, many of my colleagues were looking at the application of the process algebras to reason about biological processes, looking at cell signaling regimes and other kinds of immunological response, cancer, disease states, these kinds of things. And what they found was that the pi calculus and the ambient calculus were both quite useful in reasoning about biological processes. In particular, my colleague Corrado Priami, who heads up the Trento Research Lab in Trento, Italy, was able to write down a description of the inflammation process in multiple sclerosis using the pi calculus. You can look this stuff up, right? I'm not joking. And was able to make predictions that were different from the ones done by the differential equations based models, which were then later verified in the lab. So that's already amazing. That's already really, really cool and worthy of investigation. But what I noticed was there were lots and lots of these boutique biological databases that were designed by these amazing biologists, right? So they were essentially reinventing computer science and data store technology because they didn't know, because they were trained in biology. And it used to really, my heart would go out to them. It's like, you need some computer scientists to sit next to you so you don't have to take on this extra burden. But I sort of contemplated this idea of translating a lot of these boutique biology databases into process algebra style representations, and then I could go search them using the kinds of types we're talking about here. So here's an example of the kind of query that we're talking about. Find me all the small molecules that when I put them, put this concentration into a biological system in this state, it will never reach this other state. In other words, find me a cure. Right? Can you see that? So I've got a cell that is going through a certain kind of signaling regime, and it can reach certain disease states. So you write that down as a pi calculus process, right? And now what you're looking for is reagents that when you add them to some population of cells in a certain concentration, it prevents it from getting into the disease state, right? So now we're using these kinds of behavioral types to do this to greatly accelerate these kinds of searches, because right now they're done in the lab, right? They use actual cell populations and chemicals.
Now this is likely to be one of those undecidable queries, and that's why you need the big iron to throw at the problem and run it so you can find these things.
Absolutely. So I just wanted to give you a sense of the scope and the scale of this, right? This is not just about the one very compelling use case, which is to type check smart contracts and make them safer. This is a much bigger program. And I want to close by giving a shout out to my PhD advisor, Samson Abramsky. His work was very much an inspiration. His PhD work was called Domain Theory and Logical Form. And essentially, he had a very similar kind of insight and algorithm. If you gave him a domain theory right? Some characterization of a model of computation. He could generate a logic. So this is kind of taking that the next step in some sense. And so I feel very beholden to Samson and his way of thinking about these kinds of things. So with that, thanks very much. Any questions about what I said? Awesome. Thanks very much.